Hi everyone, Mr. Boltri here bringing video 5.3 in which we're going to talk about the physics concept of acceleration. So first, let's review the results of the ball on the Incline Lab. So this is the results from the example data, and hopefully your results look at least a little bit like this. So when we gather all of our data and graph it, we get a shape like this. And if we were to try to draw a line of best fit, we would notice that this line of best fit is not good to draw on this data because this data is kind of curving. We're seeing the curve. And so a line is not a good way to represent a curve. Instead, we can use Desmos to draw a curve of best fit, which you can see is a much better representation of our data. So normally, if we had linear data, we would write the equation. But since our data is curvy, we're going to have to do one of two things. We can either linearize it so that we can get the equation, which is a great thing to do, but not what I want to do right now, because what I would rather do instead is actually look at what's happening with the slopes of the tangent lines. So in order to do that, we're going to have to draw a bunch of tangent lines. So here I have drawn a tangent line. I actually made Desmos draw me a bunch of tangent lines so we could look at it. And we're actually going to look at what that looks like as Desmos draws a bunch of tangent lines. So it's going to start by drawing the tangent line at 0 seconds, and then it's going to draw the tangent line at a bunch of the other seconds too. So I can go through this video and I can pause, and this looks like the tangent line right at 2 seconds because it only touches the curve right there at 2 seconds, and then is a tangent line at 2 seconds. I could go ahead a little bit more, and there's the tangent line at 3 seconds. So what I want you to think about, and we're going to watch the video one more time, is what I want you to think about is what is happening to the slopes of the tangent lines, or just what in general is happening to the tangent lines as the time goes on. So that's 0 seconds, 1, 2, 3, 4. What are you noticing is happening with our tangent lines? Then the other question that I want to ask you is, well, okay, so we draw the tangent line. This appears to be right at 3, maybe 3.5 seconds. So this is the tangent line at 3.5 seconds. Well, if we were to find the slope of that tangent line, remember all the way back from unit 2, what was the meaning of the slope of a position versus time graph? Well, we know that slope is going to be rise over run, so centimeters over seconds, centimeters per second. Centimeters per second is a unit of velocity. Therefore, slope is a unit of velocity. And the other thing that's really important for you to remember, or for you to notice about the slope of the tangent lines, if we go back to that video, is that as time goes on, the tangent slopes were getting steeper and steeper and steeper. So if the slope means the velocity and the slope is getting steeper and steeper or bigger and bigger, what does that mean in terms of the velocity of our ball as it was rolling down the incline? Well, putting these two pieces of information together should make it pretty clear that the ball was speeding up as it was rolling down the ramp, which just makes sense. If you go back and you think about anything rolling down a hill, it's going to get faster and faster and faster as it's rolling down that hill. We can see this in the graph because the slope gives us the velocity, and the slopes are getting steeper and steeper and steeper as we go through time. But we might be interested in not just looking at how the slopes are changing qualitatively, but actually ascribing some numbers to that process so that we can see in terms of numerically how the velocity is changing over time. So I've chosen just some times, a half a second, 1.5, 2.5, 3.5 seconds. And what I'd like to do is I'd like to know what is the velocity at those times. But just remember the definition that we said from last semester, there's two kinds of velocity. There's average velocity, which is if you have it over a time interval. And then there's instantaneous velocity, if you're talking about the velocity at one instant or one time. So because this is 0.5 seconds, it's going to give us the instantaneous velocity at that time. And when we draw the tangent line, we know that tangent lines tell us the rate of change at a time or at a moment on the graph. So that's another reason why it's going to be the instantaneous velocity. So in order to find the instantaneous velocity at a 0.5 or 1/2 of a second, we have to draw a tangent line right there at 1/2 a second. And then when we draw the tangent line to the curve at 1/2 a second, we can find the slope of that tangent line by choosing 2 points on the line. Maybe this one might be good, and then this one right here. And when I do the rise over run of those 2 points, I find that at half a second, the instantaneous velocity was 6 centimeters per second. So now I can do the same thing, except I would need to draw a new tangent line, this time at 1.5 seconds, which is right here. So this is my new tangent line at 1.5 seconds. When I draw the tangent line again, the slope of a PT graph is the velocity. So when I find the slope of this line, maybe using this point is a good one, and this one, and then I find the slope is 18 centimeters per second, which is the instantaneous velocity. And I can do that for 2.5 seconds and 3.5 seconds too. And then I get all of my instantaneous velocities at all my different times. So hopefully by this point, you are recognizing that if you have a nice data table like this with a bunch of information, one really useful thing that we can do with it is graph it. But let's be very careful, because before we've been looking at position versus time graphs. And now I'm going to switch to a new kind of graph. So this is, we're going to do a velocity versus time graph. So here I have my instantaneous velocities, and then we're going to see how those change as time goes on by graphing these 4 data points. And when I do graph them, I get a graph that looks like this. As time goes on, you can see that the velocity is increasing, because at half a second, it's a pretty low velocity, and at 2.5 seconds, it's a pretty high velocity. So as time goes on, the velocity is increasing. And actually, something that is pretty convenient about these points is when we look at it, it actually looks like it is increasing pretty linearly. So what can we do if our data looks linear for the VT graph? Well, hopefully you know by now that we can draw a line of best fit. And with that line of best fit, we can actually find the equation by doing y equals mx plus b. Y is the velocity, m is the slope, x is the time, and b is my vertical intercept, which appears to be 0. So that would give me an equation of v, the velocity, equals 12, the slope that I calculated, times t plus 0. And you calculate the slope by choosing 2 points. Now be very careful. The slope of this graph is not the velocity, because this is a velocity versus time graph. The only time that slope gives us the velocity is for a position versus time graph. So what can we do now that we have written the equation? Well, equations are really useful because they allow us to make predictions, but we can also analyze them by looking at the meaning of the slope and the vertical intercept. Let's start with the vertical intercept. So this vertical intercept plus 0 really means that at 0 seconds, the velocity was 0 centimeters per second. All that means is it's the initial velocity. It's the velocity at 0 seconds, which is good because the object started at rest. Our data will look a lot different if instead of letting the ball go, just letting the ball go and letting it roll down the ramp, I gave it a push down the ramp. Our data would look completely different if that was the case. So it's important that our vertical intercept is plus 0, because that means that we ran the experiment in a good way and released the object from rest. Now, the more interesting thing is the slope. Well, notice that I have a slope value of 12, but sometimes it's hard to figure out what the slope means unless we look at the units. So to look at the units of the slope, we calculate slope by doing rise over run. My rise is centimeters per second, and my run is seconds. So the units of my slope are going to be centimeters per second divided by seconds. Now, a lot of times people will say, oh, the seconds cancel, and that equals 12 centimeters. But if you actually write it out using the divided by symbol instead of this slash, you'll notice that it's actually multiplying by the reciprocal, and these seconds do not cancel out, because this is basically in the denominator, and this is in the denominator as well, so they do not cancel out. So what does 12 centimeters per second divided by seconds mean? Well, let's think about it. Centimeters per second is a unit of velocity. Seconds is a unit of time. So this is basically, we could write this as 12 over 1, 12 centimeters per second, which is the unit of velocity, over 1 second, which is the unit of time. So if we look at my graph, it started at 0 centimeters per second. And then 1 second later, which is right here, was the new velocity. It appears to be 12 centimeters per second. What about 1 second after that? It seems to have increased. It's gone up another 12 centimeters per second. So what this actually means is it's how much the velocity, centimeters per second, changes for each 1 second. And so we don't have to read this out every time. How much the velocity changes every 1 second. Scientists invented a vocabulary word to mean this exact thing. And that vocabulary word is called acceleration. Acceleration is defined as how much the velocity changes each 1 second. It's a change in velocity with respect to time, or per unit time. And when I say unit time, I mean 1 second or 1 minute or 1 hour. That's a unit of time. So acceleration is how much the velocity changes each 1 second or per unit time. And it's the slope, but not the slope of any graph. It's the slope specifically of a velocity versus time graph. So the most important thing to take away from this video is that acceleration is the slope of a velocity versus time graph. What it means is how much the velocity changes each 1 second, or sometimes it might be 1 minute or 1 hour or whatever, but most of the time it's going to be 1 second. And the units of it are something like a unit of velocity divided by a unit of time, since it is a change in velocity over a change in time. And this does simplify to meters per second squared, which you may have seen before, but I'm not going to write it like that because meters per second squared doesn't mean anything to me, but meters per second divided by seconds tells me that this is a unit of velocity divided by a unit of time, which reminds me that the definition of acceleration is how much the velocity changes per each 1 second. So this is Mr. Boltri wrapping up video 5.3. Please let me know if you have any questions, either by writing it in your notes or letting me know at the beginning of our next class. We're going to do some practice problems with acceleration, but until then, go Bears.